Hi everyone, welcome to Go Classes. In this session, we will study this concept, constructing total order from partial order. How to convert partial order to total order. This is what we need to study. This is a very simple concept, simple to understand. And there are two gate questions based on this concept. Okay, and one gate question came in 2024. So recent gate question is there based on this concept. So we will do the complete analysis of this concept. Let's start. Let me tell you that all the following topics are same. So in the gate exam or in any exam, they can ask you same question in 5 different ways. All the following, you can read all the following, they are same. All these things are same. What I'm saying that constructing total order from partial order, that is same as finding total order that contains a partial order. That is same as topological sorting of partial order. That is same as linearization of partial order. And that is same as compatible total ordering of a POSET. So we will study, don't worry. One by one, we will see all of these. We will see all these 5 things we will see. And at the end, you will see that all these 5 things, all these 5 concepts, they are same. So remember, in the gate exam, same question they can ask you in 5 different ways, because these 5 concepts, they are exactly same. Okay, so for example, if they ask you what is the total order that contains a given partial order, a partial order will be given to you and the question will ask you find a total order that contains this partial order. Then remember what you need to do. Then all you need to do is just find the topological ordering, because they are same. But how they are same, we need to prove it, right? That proof we will see in this lecture. So in this lecture, we will see what these 5 concepts are, and we will see that all of them are same. Okay, now let's start. Before we start, I want to tell you, I need to teach you this concept. This is basically a small prerequisite. First we need to study what is topological order. This is a concept that you will study in the algorithm subject. Okay, this is, I can say, this is a concept for algorithm subject. There you will study this concept in a very detailed way. But here, what I need, I will teach you. Okay, I will teach you how to find a topological order. Okay, topological order, how to find this. This is what I will teach you. Okay, so first of all, let me tell you what is a directed acyclic graph. The name itself is telling you this is a directed graph without any cycle. Okay, very simple. So what is a directed acyclic graph? In short, you can call it DAG. Okay, DAG. In short, we will call it DAG. Now, what is directed acyclic graph? This is a directed graph which has no cycle. Okay, there is no cycle. Very simple. So a directed graph which has no cycle is called directed acyclic graph, or you can call it DAG. Okay, for example, look at this graph. Is this directed graph? Yes, this is the directed graph. You can see all the edges, they have direction. For example, this edge is from E to H. Okay, you can see this edge is from A to B. This edge is from B to C. Okay, so this is a directed graph. You tell me, is this directed acyclic graph? Is there any cycle in this graph? Do we have any cycle? Okay, like this. Is there any this type of cycle do we have in this graph? Is there any cycle like this in this graph? Tell me. So you can see this. Yes, this is a directed acyclic graph, right? Okay, this is a directed acyclic graph. You can easily see there is no cycle here. Okay, for example, you can see, okay, this edge is there, then this edge is there. Now you can see there is no cycle. Okay, there is no cycle because this edge is like this. Okay, so you can easily see that this is a directed acyclic graph. There is no cycle in this graph, you can easily see. Now, what about this graph? Is this directed graph? Yes, this is a directed graph. You can see every edge has a direction. From task 2 to task 3, there is edge. Okay, and there is edge from task 1 to 3, and also from task 3 to 1. Now you tell me, is this a directed acyclic graph? This is not a directed acyclic graph, right? Okay, this is not a DAG. What is the reason? Because there is a cycle. Because there is a cycle, you can see there is a cycle like this. Okay, you can easily see that you have this kind of cycle. This type of cycle you have. Okay, so very easily you can see that this is not a directed acyclic graph. Is this clear? Because there is a cycle. Now, what about this graph? Is this directed acyclic graph? You can see this is a directed graph, but do we have any cycle in this graph? Let's check it. You can easily check. This is a directed acyclic graph. Okay, you can easily check it. Yes, this is a directed acyclic graph. You can see, for example, there is no cycle. Okay, like here, there is A's like this, there is A's like this, but there is no A's like this, right? Yes or no? From E to F, there is no A's. Similarly, for example, there is A's like this, there is A's like this. Okay, but you can see there is no A's, there is no A's like this. Okay, you can easily see. Just spend maybe 2 minutes, you can look at this graph and you can see there is no cycle. So this is a directed acyclic graph because there is no cycle in this graph. Okay. Now let's see what is topological ordering of a directed acyclic graph. Remember, you must have a directed acyclic graph, a directed graph without cycle. Now, if you have a directed graph without cycle, then what is topological ordering of this graph? For example, if I give you this graph and I ask you what is topological ordering of this graph? If I give you this graph and then I ask you what is topological ordering of this graph? Now the name, you can see ordering. Okay, topological ordering. So remember, this is a linear ordering. What is topological ordering? This is a linear ordering of elements of this directed acyclic graph. A graph is given to you. A directed acyclic graph is given to you. What is topological ordering? That is a linear ordering of elements of this directed acyclic graph such that if there is A's from U to V, then in this order, in this topological order, this V appears after U. Is this clear? Okay, very simple point that in your graph, let's assume you have a directed acyclic graph G. This is your graph G. In this graph, let's assume this type of edge is there from U to V. Let's assume there is edge. Okay, then in this situation, in the topological ordering, what will happen? In the topological ordering, remember, topological ordering is a linear ordering. Okay, so the elements of this graph you will put in a linear order, such that if there is A's from U to V, then remember, in this order V comes after U. Okay, it means that this cannot happen. Can it happen? Tell me that V is coming, then after some time U is coming. This can never happen. Okay, this can never happen. If there is A's from U to V, then what will happen? Then this V, this comes after U. Okay, it can come immediately or it can come after some time. Okay, basically this V should happen after U. This should happen. Okay, very simple. So this is your topological ordering. This is the definition of topological order. So topological order is a linear order of elements of graph. So if this graph is given to you, then topological ordering means this is a linear order. All these elements A, B, C, D, E, F, all these elements you have to put in a linear order such that if there is A's from E to A, for example, you can see there is A's here from E to A, then in the linear order, in the topological order, this A will come after E, or I can say this E will come before A. Okay, so very simple point. I hope you understood. So let's see, if I give you this directed acyclic graph, then can you find the topological order? I have given you this directed acyclic graph is given you. Now you tell me, if I want to find what is topological order, can I start, for example, few things? I am asking few things. You tell me in the topological order. Topological order is a linear order, remember. Okay, this is a linear order of elements. I need to put the elements in a linear order. There are how many elements? Total 6 elements. So I need to create this type of order. I need to create. Okay, a linear order I need to create because topological order, that is a linear order. I already told you. You can see this is a linear ordering. Okay, so I need to create a linear order. Now you tell me a very simple point. In this linear order, can it happen that A is coming before E? Is it possible that A is coming before E? Is it possible? Is it possible that A is coming before E? No, this is not possible. Okay, because in the topological order, what should happen? If there is A's from E to A, then A must come after E, or I can say E must come before A. Very simple. So you cannot have this type of situation. Okay, tell me one more thing. Can it happen that A is coming A is coming after D? Can it happen that A is coming after D? Again, this cannot happen because if there is A's from D to A, then D should come before A. Very simple point. Yes or no? Okay. Now you tell me one more thing. Is it possible that starting vertex is B? Can I start this linear order with B? Topological order is a linear order, right? Okay. Now I'm asking that this linear order, total 6 elements are there. Can I start my sequence with element B? Is it possible? This is not possible. What is the reason? Tell me what is the reason. Let me know. I cannot start with B because before B, C should come. Before B, F should come. Do you agree with me? Yes or no? Very simple that before B, C should come. Before B, F should come. Okay. So this should happen. This should happen. So I cannot start with B. Now you tell me from where to start. Now I want to create a topological ordering. Topological ordering I want to create. And remember, topological ordering is a linear ordering of elements. So I need to put all these elements in a linear order. Total 6 elements are there. I want to get a linear order. And the condition, remember the condition is like this. If there is age from D to E, then D must come before E. If there is age from F to D, then F should come before D. Okay, so what should be the starting point? The starting point must be a vertex without any incoming edge. Yes or no? The starting point should be a vertex without incoming edge. So remember, the starting point, either this can be F or this can be C. So very simple point, either the starting point can be F or the starting point can be C. So very simple point, this starting point, either this can be C or this can be F. Okay, because remember, the starting point will be a vertex with no incoming edge. You can see F comma C, they have no incoming edge. These two vertices, okay, look at these two vertices, they have no incoming edge. So the starting point can be either C or F. Okay, you can put any of them, it doesn't matter. You can put any of them. So now let's see, if I put C, let me assume that I'm putting C. Now what you do, if I'm putting C, then delete this C. Okay, then C is gone. Okay, this C, this is gone. Okay, now delete this C. Just delete it. So very simple. If I start with C, then I can delete this C. Okay, now forget about C. Delete this C. Now you tell me what can be this next element. Tell me what can be this next element. Let me know. This next element, what it can be. So again, the next element, remember, it cannot be B because before B, F should come. Yes or no? So the next element has to be F. The next element, remember, the second element cannot be B. Why? Because before B, F should come. There is age like this. Okay, there is age. Here you can see this age. So before B, F should definitely come. Okay, so I can say the second vertex must be F. Is this clear? Very simple. Okay, so this must be F. Now, after that, what should happen? After that, so now you can delete F also. Okay, what you can do? Now you can delete F also. So let me delete F. Now, remember, the second vertex is F. Now delete F. Okay, all these things are gone. Delete F. Now F is gone. Okay, because already C comma F are covered. Now delete F. Now you tell me what can be the next point. The next vertex either can be D because there is no incoming edge now. Now D has no incoming edge. I can say that this D, this has no incoming edge. This B has no incoming edge. Okay, so these are the vertices with no incoming edge. There is no incoming edge. Okay. So I can put either D or I can put B. Okay, so remember, it will happen like this. If I put D, now you tell me what will happen. Let's assume I am putting D. If I am putting D, then what will happen? Tell me. So you delete this D also. Now this D is also gone. If I am putting D, then this D is also gone now. Okay, now this is also gone. Now you tell me what will be the next vertex. The next vertex either can be B or E. Yes or no? Either it can be B or it can be E because now there is no incoming edge in B and there is no incoming edge in E also. Okay, so very simple. Now what I can do? I can take, for example, B I can take. Now you delete this B. Okay, now I have to take E. I have to take E and then you delete this E also, then you delete this E also. Okay, now I can take A. So this is a possible topological order. Is this clear? This is one of the possible topological order. Possible topological order. Is this clear? So remember, this is one of the possible topological order. Can you create other topological orders? Okay, let me see. Okay, let me create some topological orders. You tell me which of them are topological orders. Okay, so there is C also. You already know there is C here. This is your graph, right? Yes or no? Correct. So this is our graph. Now you tell me what are the topological orders. You give me, I'm giving you. Tell me, is this a topological order? If I write, for example, if I start with F, then I take E, then I take D, then I take C, B, A. Is this a topological order? Let me know. On your screen, I have given you this order. Is this a topological order? This is not a topological order. Tell me why. Where is the violation? Tell me about the violation. The violation is very simple, that D must come before E. Yes or no? The violation, let me tell you the violation. The violation is that, remember, D must come before E. Yes or no? This should happen. D must come before E. This is the violation. Is this clear? This must happen. So, very simple that this is what should happen. Now you tell me, is now let me, so remember, this is not a topological order because there is A's from D to E. So D must come before E. There is violation here. At this point, there is violation. Okay. Is this clear? Very simple point. Now you tell me, is this a topological order? If I do, for example, F, then D, then E, then C, B, A, is this a topological order? Let me know. On your screen, is this a topological order? Yes, this is a topological order, right? Okay, you can easily see what is happening. See, first you are deleting F. First you are deleting F. Now can I take D? Tell me. See, one by one I am telling you. See, first I am deleting F. I can start with F because F has no incoming edge. There is no incoming edge. So I can start with F. Now I am deleting F. Now can I take D? Tell me, can I take D? Yes, I can take D. Now delete D. Now can I take E? Yes, there is no incoming edge. So I can take E. Now can I take C? Yes, I can take C because there is no incoming edge in C. Now can I take B? Yes, I can take B. Then can I take A? Yes, I can take A. Did you understand? Please tell me. Let me know. So yes, this is a topological order. Let me give you another topological order. For example, I can start with F, then I can take C. Okay, then I can take D, then I can take B, then E, A. Is this a topological order? Let me know. Again, yes, this is a topological order. Very simple. See, very simple. I'm starting with F. So delete F. So you delete F. Okay, I have deleted F. Now, can I take C? Yes, I can take C because C has no incoming edge. I can take C. Now, can I take D? Yes, I can take D because D has no incoming edge. Can I take B? Yes, B has no incoming edge, so I can take B. Then I can take E because E has no incoming edge. And finally, I can take A. So this is the topological order. I hope you understood. Okay, is this clear? So this is how you can find topological order. So remember, many topological orders are possible. I hope you understood. So this is the simple point. Remember, if I give you a directed acyclic graph, in the directed acyclic graph, you must have directed acyclic graph. Okay, if you have directed acyclic graph, then what you can do to find topological order, all you need to do, very simple, that remember, topological order is a linear order. So the elements of this graph you are putting in a linear order. Okay, and what should happen? If there is edge from U to V, then V should appear after U, or I can say U should appear before V. This type of ordering is called topological ordering. Okay, and the algorithm to find this topological ordering, that is called topological sort. Okay, so this ordering, remember, this linear ordering will be called topological ordering, and the algorithm to find this topological ordering, that is called topological sort. Very simple. Okay, so this was our graph, and for this graph we have already seen some topological orders. We have already seen. Okay, I hope you understood. Is this clear so far? Please tell me. Okay, now let's move on. Can I give you one homework? Can I give you one homework? That is, what is the number of topological orderings for this directed acyclic graph? Find all topological orderings. Okay, how many topological orderings are there? So let me give you this homework. Okay, that find number of topological orderings. Number of topological orderings possible. How many topological orderings are possible? Because you can have many different topological orderings. Okay, so find number of topological orderings of this DAG. Okay, is this clear? So put your answer in the comment. Please do that. Okay, so this is your directed acyclic graph. Find the total number of topological ordering possible. What is the total number of topological order that are possible? You find that and put your answer in the comment. Okay, let's move on. Now let's see the algorithm. Okay, how to find the topological ordering. I think you already know the algorithm now. What we will do? We will start with the vertex which has no incoming edge. Yes or no? So we will start with the vertex which has in degree 0. In degree 0 means there is no incoming edge. Very simple. So start with the vertex that has no incoming edge. Start with that vertex, delete that vertex, then again repeat the same procedure. Yes or no? Until no nodes are left. So the algorithm is very simple. Start with the vertex which has no incoming edge. You start with that vertex, delete that vertex, then again you repeat the same procedure. Okay, is this clear? Like this you can repeat the same procedure and you can find what is the topological order. Okay, now let's solve this question. This is gate 2016 question. Consider the following directed graph. The number of different topological orderings of vertices of this graph. First of all, you tell me, is this graph directed acyclic graph? The question is saying this is a directed graph. Is this a directed acyclic graph? Is there any cycle in this graph? There is no cycle. This is a directed acyclic graph, right? Okay, this is a directed acyclic graph. So remember, this is important that this is directed acyclic graph, because in a directed acyclic graph, you can find topological orderings. Okay. Now, what we need to do? The number of different topological orders we need to find. Okay, so let's find this. In this graph, you tell me what will be my starting point. I want the number of different topological orderings. What will be my starting point? Starting point will be a vertex with no incoming edge. Which vertex has no incoming edge? Tell me. Yes, this vertex has no incoming edge. Correct? Okay, you can see this vertex has no incoming edge. So this vertex will be my starting point. Correct? Agree? So very simple. This will be my starting point. So the starting point will be A. Now there are total 5 more vertices, because remember topological ordering, that is a linear order. What I need to do, these vertices, these elements I need to put in a linear order. And what the condition for topological order? The condition is, if there is edge from B to C, then B should come before C. If there is edge from D to E, then I can say E should come after D. Okay, so this is the condition. So you can see the starting point will be A. Very simple. Now what you do, once this A is done, okay, this A will be the starting point. Now you delete this A. Now just delete this A. Now you tell me which vertices have no incoming edge. Delete this A and you tell me which vertices have no incoming edge. You can see that. Now this vertex has no incoming edge. Also this vertex D has no incoming edge. So now I can take either B or D. Yes or no? What I can do? Either I can take B or I can take D. Okay. Let me take B. Let me take B first. If I'm taking B, now you delete this B also. Okay. Now you delete this B. Now you tell me what you can do. So after this B, what you can do? If I take this B, then after this B, if you delete this B, now either I can take C or I can take D. Okay. If I take C, then I have to take D, E, F. So this is one possible order. Correct? Very simple. Okay. Now another possible order is, remember, another possible order will be, you are starting with A, then you are taking B. Okay, I am taking B now. Now let me cover all the cases where I'm taking AB first. Okay, I will cover all the cases where I'm taking AB first. So if I take AB first, now delete this B. Now what I can do? I can take D first. Okay, I can take D first. Now if I delete D, now there are two things. Either I can take C first or I can take E first. So remember, either I can take C first, then I will get this, or what I can do, I can take E first. Then this is what I will get. So these are the orders you will get when you are starting with AB. Okay, if you start with AB, then this is what you will get. Now if you start with AD, now what will happen? Okay, after deleting A, now if you take D, then what will happen? Very simple. This AD, now delete this D. Then what you can do? You can take E. Okay, then automatically it will be BCF. Similarly, after A, if I delete this D, okay, now you can see that I can take B, no problem. I can take B. But remember, after deleting B, now either I can take C or I can take E. Okay, so I will get these either CEF or ECF. So these three. So finally, the answer will be what? Answer will be total 6. Is this clear? The answer will be that is total 6. Is this clear? Please tell me. Let me know. Okay. So very simple. This question is not complicated. All these topological ordering questions, they are actually very easy questions. Okay. So like this, you can easily do. Okay. Now let's move on now. So remember, for this graph, this is a directed acyclic graph. For this graph, the number of different topological ordering, that will be actually 6. Okay. So quite easy. Now, this is your homework question. This graph is given to you, and I think, yes, I've already given you this question as a homework. You need to find the total number of topological orderings. Yes or no? This is what you need to find. How many topological orderings are there? This is what you need to find. This is a question from Stanford. You can read this question. Okay. Basically, for this directed acyclic graph, this is a directed acyclic graph. You need to find the total number of topological orders. Okay. So just find this. So students are asking, is there any formula for it? Let me tell you, the answer is no. Okay. If a random directed acyclic graph is given to you and the question is asking how many topological ordering are there is no direct formula for it. Okay, that is one thing. Second thing, you will study this in detailed way in the algorithm subject. Okay, so I am just teaching you what I need. Are you getting my point? What I need, I am teaching you that if there is a directed acyclic graph, then what is a topological order? That is what I am telling you. Remember, the same concept you will study in the algorithm subject. This gate exam question you will again solve in the algorithm subject. Is this point clear? Please tell me. This question, this gate exam question that we have done, the same question you will again solve in the algorithm subject. When Sachin sir will teach you algorithm subject, then this topological ordering will again come. Topological sorting, topological ordering, all these concepts will again come. Don't worry. Okay. But remember, there is no direct formula. If I give you a random directed acyclic graph, a random DAG, if I give you DAG, then there is no direct formula. There is not a simple formula which can find the number of topological ordering. Okay, you have to go manually. Is this clear? Maybe some smart method you can apply depending on the graph. Okay, depending on the graph, you can apply a smart method. For example, here you can apply a smart method. Let me tell you the smart method. Okay, but don't worry if you don't understand. Do not worry, because this concept, as I told you, you will study in the algorithm subject. So the smart method is, see, you have to start with A and you have to finish at F, right? Tell me, is it possible that after F something can come? Tell me, is it possible that after F something can come? No. Okay, you have to start with A, you have to finish at F. Now there are four positions. There are four positions. In these four positions, you can notice that what you can do, let me tell you. This is the condition that, see, delete this A, delete this F. Yes or no? Because first A will come, then last F will come. This you already know, right? Agree with me? The starting point will be A and the ending point will be F, because remember, after F, nothing can come. Okay, before F, everything will come. Before F, all these nodes will come before F. So now what you do? Delete A comma F. Now there are four positions. And you can see only this is the relationship. That in these four positions, B should come before C, D should come before E. So what you can do, very, very simple. In these four positions, you can select two positions for B comma C. Are you getting my point? There are four positions. From these four positions, you can select two positions for B comma C. Is this clear? For C2. This you will study in the combinatory subject. I hope you already know. If you do not know, don't worry. Do not worry. Forget about it. Do not worry. I'm just telling you, if you already know what is combinatorics, what is 4C2, then you can just listen to my explanation. You can see there are four positions. From these four positions, you can select two positions for B comma C. Okay, for B comma C, from these four positions, you can select two positions. Let me assume I am selecting these two positions. Okay, if I select two positions, then how many ways B comma C I can put? Once I have these two positions, from these four positions, I am selecting two positions. Yes or no? For B comma C. Now, once I have selected two positions, for example, these two positions, let's assume I have selected these two positions. Now, in how many ways I can put? Only one way, because B should come before C. Okay, so B should come before C. Right? Yes or no? B should come before C. And in the remaining two positions, what will happen? There are remaining two positions. There are remaining two positions. From these remaining two positions, I can select two positions for D comma E. Okay. So there are two positions remaining. From these two positions remaining, I can select two positions for D comma E. How many ways I can put D comma E? Only one way, because D should come before E. So your answer will be what? Your answer will be 4C2 multiplied by 2C2. 2C2 is only 1, and 4C2, that is 6. Okay, so this is another method. What I'm telling you, if a random directed acyclic graph is given to you, then there is no direct formula to find the topological ordering, to find the number of total topological ordering. Okay, there is no direct formula, there is no simple formula. But depending on the question, you can apply some clever trick. If you do not apply the clever trick, then also you can solve this question, right? Yes or no? If you do not apply this method, this combinatorics method, if you do not apply, then also very easily you can solve this question like we have already done. Okay, is this clear? So I hope you understood. Now let's move on. Now, because our main topic, what is that? Remember, for this lecture, in this lecture, our main topic is not topological ordering. Our main topic is to convert a partial order into total order. That is our main topic. And whatever information I have given to you for the topological ordering, that is enough. What is topological ordering? Okay, how to find the topological ordering? That is what we need. I hope you understood. Is this clear? What is directed acyclic graph? It is a directed graph without any cycle. Now, if you have a directed acyclic graph, then in that graph, you can find the topological ordering. What is the topological ordering? It is a linear order of vertices such that in the graph, if U is coming before V, or in the graph, if there is A's from U to V, in the graph, in the directed acyclic graph, if there is A's from U to V, then in the topological order, U will come before V. So very simple. This is the concept. Okay. I hope you understood. Now, this is your homework question. Please pause the video, solve this question, put your answer in the comment. The question is from Stanford. Directed acyclic graph is given to you. The question is asking how many different topological ordering are there. Okay, so write your answer in the comment. Okay, comment your answer. Now let's move on. Now let's see constructing total order from partial order. This is our main topic. Okay, so let's study this topic. How to construct a total order from a partial order. Means a partial order will be given to you, or a hash diagram will be given to you, and the question will ask you find the total order. So let's see what is this concept. Let's see this real life scenario. Let's assume there is a new student. The new student comes to you and this student is asking you the order in which to study these subject. There are some subject like theory of computation, compiler design, C language, data structure, algorithm, digital logic design, and computer organization. Okay, so these are the subjects. Now there is a new student, and this new student is coming to you and asking you the order in which to study these subject. Now you are giving the following order. What you have done, you are giving this following order based on the prerequisite. You are saying that before compiler design you should study theory of computation, yes or no? Okay, what you are saying, you are saying before data structure you should study C language, before algorithm you should study data structure, before computer organization you should study digital logic. Okay, so this is what you have given. Okay, from your experience, this order you have given. Tell me, is this a partial order or is this a total order? This is the order that you have given. You are giving this order. Okay, this is the order you are giving. Is this a partial order or is this a total order? Yes, this is a partial order, not a total order, right? Yes or no? Why this is not a total order? Tell me. Tell me, what is the reason this is not a total order? Because you can see there is no order between compiler design and data structure. Do you agree with me? I can say that compiler design and C language, they are not comparable. Okay, you can see that this compiler design comma C, they are not comparable. Not comparable. Or I can say that there is no order between compiler design and C language, yes or no? Or I can say there is no order between algorithm and digital logic design, yes or no? Agree with me? Okay, so this is a partial order, but this is not a total order, because you can see these two subjects, they have no order. Okay, you are not saying anything about these two subjects. In which order I should study these two subjects, you are not saying anything about that. So you can see these are not comparable. Okay, is this clear? So very simple, I can say if I give you this order, that before compiler design you should study theory of computation. Okay, before data structure you should study C, and before algo you should study data structure. Digital logic design you should do before computer organization. Now this is a partial order. This is a partial order. Why this is not a total order? This is not a total order because there is no order between C language and TOC. Okay, I can say this is not a total order because there is no order. There is no order between, for example, TOC comma C language. Okay, total order means there should be order between every two elements. Yes or no? The definition of total order, what is that? Total order, that means you should have order between every two elements. Every two elements must be comparable. Total order means every two elements have order. This is the definition of total order that you already know. What is total order? Total order means every pair of elements are comparable. I can say that every pair of elements have order. Every pair of elements have order. Okay, whatever two elements I give you, they have order. This is the definition of total order. So you can see this order that you are giving, this is a partial order, but this is not a total order. Now you tell me, after you give this partial order, okay, this is the partial order that you have already given. This student wants to study one subject at a time. Okay, this new student wants to study one subject at a time. Tell me, if I want to study one subject at a time, then I need a total order or not? Just tell me this point. If I want to study one subject at a time, one subject, then another subject, then another subject, then another subject, if I want to do this, then I need a linear order or not? Do I need do I need a linear order? Yes, I need a linear order. So this student wants to study one subject at a time. So this student needs a linear order. So tell me, how many linear orders they are compatible with this given partial order? Okay, from this information, how many linear orders I can create which will satisfy this criteria, which will satisfy this constraint? How many linear orders I can create? I want to study one subject at a time. How many linear orders I can create which will satisfy these conditions? Some conditions you are giving, and these conditions must be satisfied. Agree with me? Okay. So this is what I'm saying, that TOC before compiler design, C language before data structure before algorithm, digital logic design before computer organization. Okay, these basically these are conditions, I can say. Yes or no? These are basically the conditions, or I can say these are basically the partial order. Now, I want total order which will satisfy these conditions. Okay, I want total order which is compatible with this partial order. What I want a total order. Total order means linear order. I want a linear order which is compatible with this partial order. With this given partial order. Okay, so this is what I need. You tell me a very simple thing I'm asking you. Okay, in my linear order, is it possible that I can do algorithm before C? Is it possible I can do algorithm before C? Is it possible? In my linear order, okay, can this student study algorithm before C? No. Okay, of course no, because this is not compatible with this given partial order. See, this partial order is saying that before algorithm you should do C, before algorithm you should do data structure, before data structure you should do C. Okay, so very simple. This I can say this is not possible, or I can ask you, can I do algorithm before data structure? Again, this is not, this is invalid. Yes or no? This is invalid. So very simple thing. Now you tell me, if I'm asking you, find total order, find a linear order which is compatible with these conditions, which is compatible with this partial order, then basically what you are finding, what is coming to your mind, what are you finding now? You are basically finding the topological order. Yes or no? Do you agree with me? You are basically now you are finding the topological order. Okay, what you can do, you can do in this order. For example, you can start with C, no problem. Okay, before C there is nothing, so you can start with C. After C, what you can do, you can do data structure, no problem. After data structure, let's assume you want to study TOC, you can do that. After TOC, let's assume you want to study digital logic, you can do that. After that, you want to study algorithm, you can do that. After that, you want to study computer organization, and then you want to study compiler design. So this order, tell me, does this order follow these conditions? This linear order, does it satisfy these conditions? Or I'm asking, this linear order, this total order, is it compatible with this partial order? Yes, this is compatible. Okay, so in this order, the student can study. This new student who is coming to you, this student can study in this order. Agree with me? Okay, can you give me some other order? Some other order, can you give me? Yes, for example, you can start with TOC, then you can study compiler design, then you can study digital logic design, then you can study C language, you can study data structure, you can study algorithm, and then at the end you can study computer organization. This is also fine. Okay, of course you can create many different total orders. For example, this linear order you can create, you can start with C, then data structure, then algorithm, then TOC, then compiler design, then digital logic design, and then computer organization. This is also possible. Okay, I hope you are getting my point. So remember, can I say that finding linear order compatible with a given partial order, that is same as finding the topological order? Can I say? Is this statement true or not on your screen? Constructing a compatible total order from a partial order is same as finding the topological order. Yes or no? Is this clear? Very intuitive. With intuition, I am teaching you this concept. I hope you understood. Is this intuitive? Tell me intuitively, are you understanding? And will you ever forget this simple concept? Very simple. That if I give you a partial order and I ask you what is compatible total order. Okay. From this partial order, you tell me what is a compatible total order, then that is same as finding the topological order. So this is the note. Okay, let's move on. Let me give you another scenario. Another real life scenario I'm giving you. Your company requires you to do 6 tasks. There are total 6 tasks. 1, 2, 3, 4, 5, 6 on your screen. You can see these are the tasks. Okay, your company. Now, some of these tasks can be started only after other task is finished. The question is saying some of these tasks can be started only after completing the other task. For example, dependency is shown in the graph. In this graph, dependency is already shown. Basically, this graph is saying that before attempting this task 2, you should complete task 1, right? Yes or no? For example, before completing task 3, you should complete task 6. Before starting task 4, you should complete task 2. Okay, so this is the point that you need to do 6 tasks, and this dependency graph is already given to you. The graph is saying that before starting task 5, you should complete task 4 because there is dependency here. Because there is dependency here. Okay, so very simple. Now you tell me, find an order in which these tasks can be carried out to complete the project. I want to complete the project. Okay, then in which order I can complete the project? Tell me. So the answer is quite simple. What that will be? So let's see. Basically, what you need to find, you need to find the topological order. Okay. These tasks, what you can do in this order. For example, you can start with the task 1. Is it mandatory to start with task 1? Can you start with any other task? Can I start with 5? No. Before 5, I need to do 4 because you can see there is edge. Okay. So you can see this vertex has no incoming edge. Okay. Remember, this has no incoming edge. So you can start with, you have to start with 1. Okay. First, you have to do 1. Now you delete this 1. Now you tell me, what is the next thing you need to do? You need to do 2. Okay. Yes or no? Because remember, if I delete this 1, now 2 has no incoming edge. This task 2, it has no incoming edge. Okay. So you can do, after 1, you can do 2. Now if I delete these 2, okay, these are gone. Now which task can I do? Now I have to do task 4. Yes or no? Because task 4 has no incoming edge. You can see there is no incoming edge in the task 4. So I have to do 4. Now, if I delete all these, okay, now you tell me which task can I do? Now, this 5, task 5 has no incoming edge. So I must do 5, then 6, then 3. Yes or no? 5, then 6, then 3. So this is a topological order. Is there any other topological order possible? Is there any other topological linear order possible? No other linear order possible. Yes or no? No other topological order possible. Only this is the order. Okay. So very simple. I hope you understood. So finally, this is the point that if you want to find compatible total order for a partial order, then what you need to find, you need to find the topological order. Is this clear? I give you a partial order is given to you, partial order. Then you want to find compatible total order, which will satisfy the conditions of this partial order, okay, which will satisfy the order of this partial order. So if you want to find a compatible total order, then all you have to do, just find the topological order of this partial order relation. Yes or no? So this is the point. I hope you understood. Now let's move on. Now tell me the answer for this question. Accept self loop. Forget about self loop. Okay, accept self loop means forget about self loop. Can can the graph of partial order relation contain cycle? Is it possible that you can contain cycle? I am asking, the graph of partial order relation, can it contain cycle? Tell me. It cannot contain cycle. The answer will be no. It cannot contain cycle. But can you prove it? But can you prove it? Let me know. Can you prove it? Tell me. Yes, I can prove it. Okay, because of asymmetric and transitive property. Let me tell you that can can graph of partial order contain cycle? The answer is no. Okay, because of antisymmetric and transitive property. And transitive property. Okay, let me prove it. Don't worry. Let me prove it to you. Okay, I will prove that in a partial order relation, you cannot have cycle. Okay, in a partial order relation, in graph of partial order relation, in the graph of a partial order relation. Okay, in that graph, can you have this type of cycle? Tell me, is it possible? Is it is this cycle possible? I am asking, is this cycle possible? Like, okay, I am giving you a cycle, and you tell me, is this cycle possible? Like this type of cycle from A to B and from B to A. Is this cycle possible? Let me know. Please tell me. Is this cycle possible? The answer is no. Okay, because partial order relation, that is antisymmetric. That is antisymmetric. So you can never have this type of situation because this violates antisymmetric. Yes or no? Here, if you look at this, this is violation of antisymmetric property. Right? Correct? Okay, so you cannot have this type of cycle. Now you tell me, can you have this type of cycle? For example, A to B, B to C, and C to A. Is this cycle possible? Again, I have the same question. Is this cycle possible? Is this cycle possible? Tell me. In a partial order relation. Again, this cycle is not possible. Tell me why. This cycle is not possible. What is the reason? See, if you have this cycle, see, if, notice, if you have this cycle, then what will happen? Then by transitivity, you must have B to A. If you have this cycle, if this cycle exists, now what should happen? Then, by transitivity, what should happen? Tell me. What transitivity tells you? Then by transitivity, remember, B is related to C, C related to A, so B must be related to A. Yes or no? See, B is related to C, C is related to A, so B must be related to A. By transitivity, B must be related to A. Now, if B is related to A, now there is a problem. If B is related to A, now there is a problem. What is the problem now? Now the problem is antisymmetric violated. Now antisymmetric violated. So is this point clear? Let me know. So in the partial order relation, can you have this type of cycle? Graph of partial order relation. Can it have cycle? Finally, you tell me. You cannot have this type of cycle. If okay, you cannot have this type of cycle. You cannot have. Not possible. Okay. You cannot have this type of cycle. And remember, you cannot have this type of cycle. Again, this is not possible. Okay, similarly, you can easily check. You cannot have any cycle. Okay, if you have, for example, if you have this type of cycle, that is also not possible. Tell me why. Let me know why this cycle is not possible. Just tell me. Again, very simple thing. This cycle is not possible because by transitivity, what will happen? By transitivity, A will be related to D. Yes or no? By transitivity, you can see, by transitivity, A will be related to C. Okay, this will happen. And again, by transitivity, A will be related to D. So again, this is not possible. I hope you understood. So remember, in graph of partial order relation, there is no cycle possible except self loop. Yes or no? No cycle possible except self loop. Is this clear? Is this point clear to everyone? Please tell me. This can come in the gate exam. They can ask you. Did you understand the proof? For example, this proof, did you understand why I cannot have this cycle? Look at this cycle. In the partial order relation graph, can I have this cycle? This type of cycle can I have? Okay, assume you have this cycle. Just assume if, okay, please understand here. Assume if this cycle exists, then what will happen? By transitivity, you can see B is related to C, C related to A. Okay, so by transitivity, B will be related to A. And now you can see the antisymmetric property is violated. So very simple point that graph of partial order relation, no cycle possible except self loop. Forget about self loop. Don't worry about self loop. So can I say graph of partial order relation is a directed acyclic graph except self loop? Don't worry about self loop. Okay. Do not worry about self loop. Other than that, you tell me. Except self loop, the graph of partial order relation, can I say that is a directed acyclic graph? Let me know. Yes, that is a directed acyclic graph. This is the note. Okay, I hope you understood. The graph of partial order relation never contains a cycle. It will never contain cycle, so it is a directed acyclic graph. Very simple. And you can see the same proof is given in this Waterloo University. Okay, you can see the same proof is given that this is the feature of partial order. One feature of partial ordering is that it is not possible to have a cycle. Is this clear? It is not possible to have a cycle. And the same proof is given. Non-existence of cycle in the partial ordering. This is Waterloo University slide. Okay. Anyway, we have already seen the proof. So very simple that other than self loop, the graph of partial order relation will never have cycle. Okay. So I can say it is a directed acyclic graph. Very simple. Now, tell me the answer for this question. We already know that in the hash diagram, do we show the self loop? Tell me. In the hash diagram, do we ever show the self loop? No. In the hash diagram, we don't show the self loop. And all the edges are in the upward direction, that you know. That all the edges, they are in the upward direction. So can I say every hash diagram is a directed acyclic graph? Yes. Okay. So the answer again will be yes. Okay, because all the edges, they are in the upward direction and there is no cycle. There is no cycle. Okay, so I can say your hash diagram, that is directed acyclic graph, because there is no cycle. In a partial order relation, you can never have a cycle. Okay, and hash diagram is created for partial order relation. So hash diagram is directed acyclic graph. The answer is yes. Now let's move on. So this is the note. Every hash diagram, that is a directed acyclic graph. Okay, tell me the answer for this question. Every hash diagram, that is a directed acyclic graph, that is fine. So tell me, what is the element with no incoming edge? Very simple question. Every hash diagram is directed acyclic graph, that we already know. Now you tell me, the topological ordering will start from which vertex? Just tell me. The topological ordering, that will start from which vertex? That will start from vertex with no incoming edge, that you already know. Topological ordering always starts from a vertex with no incoming edge. So you tell me, which is the element with no incoming edge? Element with no incoming edge. This type of element is in the hash diagram. In the hash diagram, which element has no incoming edge? Some students are saying leaf node, root node. Tell me, in the hash diagram, do you have these words? In the hash diagram concept, root, leaf, these terminology, do we have? Tell me. We don't have these terminology. Hash diagram concept does not have these terminology, leaf, root. Forget about these. These are not even the concept in the hash diagram. In the hash diagram, we have minimal, maximal, least, greatest. These concepts we have. Okay, so now you tell me. Every hash diagram is directed acyclic graph. What is the element with no incoming edge? This is the definition of minimal element. This is the definition of minimal element. Yes or no? Some students are saying least element. That is also correct, because least element is minimal element. Yes or no? Agree with me? Some students are saying least element. That is also fine, because every least element is minimal element. But this is the definition of minimal element, that element without any incoming edge. See, what is the minimal element? The definition of minimal element, that is element without any incoming edge. This is the definition of minimal element, right? I can say element with no incoming edge. With no incoming edge. Understood? This is the definition of minimal element. Remember, every list element is minimal. That you already know. Every list element, if you have list element, then that is minimal. That we already know that every list element is also minimal. But this is the definition of minimal. I hope you understood. See, if I give you this statement, element with no incoming edge, okay, element with no incoming edge, then this is the definition of which element? Tell me, this is the definition of which element? This is the definition of minimal element. Element with no incoming edge. Agree? With no incoming edge. So you tell me one thing. Hash diagram is directed acyclic graph. On the directed acyclic graph, I can apply the topological ordering. I can find the topological ordering. Now, if I give you a hash diagram and I ask you to find the topological ordering, then you will start with which vertex? You will start from the vertex which has no incoming edge, and that vertex is minimal element. So your starting point will be what? If you want to find the topological ordering of a hash diagram, then your starting point will be minimal element. Very good. Very good. Yes or no? Then your starting point will be minimal element. So this is the note. This is your last note. Every hash diagram is directed acyclic graph. Okay, so you can find the topological order. You can find now in topological order, the starting point is a vertex with no incoming edge. In the hash diagram, this type of element is minimal element. Minimal element is the element with no incoming edge. So topological sorting starts from minimal element. Is this point clear? This is the final conclusion. That topological ordering starts from minimal element. Delete the minimal element and keep going on. So your topological ordering will start from minimal element. Let's see this example. Find all compatible total orderings. I want all the compatible total orderings for the given POSET. Tell me, when the question is asking compatible total orderings, then what you can find? Let me know. When the question is asking compatible total orderings, then what you need to find? For any POSET. For any POSET P. When I ask you compatible total ordering, then what you need to find? Tell me. We have already seen this. For any POSET P, compatible total ordering. Compatible total ordering, that is same as topological order. Okay, compatible total ordering, that is same as topological ordering. Very simple. So compatible total ordering of P will be same as topological ordering of P. So ultimately, this is what you need to find. The question is asking you find compatible total ordering, but that is same as this word. Okay, that is same as topological ordering. This is equal to topological order. Now you already know. If I want topological order, then my starting point will be vertex with no incoming edge. That also you know. In the topological order, think about it. In the topological order, the starting point is vertex with no incoming edge. Now you tell me which vertex has no incoming edge here? That is minimal element. Minimal element has no incoming edge. So you can see this is minimal, this is minimal. These are minimal. So your starting point will be minimal vertex. Minimal. Yes or no? So I can start with A. If I delete A, now what is the next thing I can take? If I start, see, I can start with A, right? I can start with A. Now delete A. Now forget about A. Now, can I take C? Can I take C? Tell me. See, if I delete A, now you tell me what is minimal here in this new diagram. In this new diagram, what is minimal? I'm starting with A. This is my starting point because A is minimal. Now, if I delete this A, I am deleting this A. Now, which element is minimal? Is C minimal? Is C minimal? No. No, C is not minimal because B is related to C. This B is related to C, so C is not minimal. So I need, this is the only minimal, so I need to take B. After taking B, now you delete this B. Now you delete this B. Now you tell me which element can I take? Now this C is minimal, D is minimal. Yes or no? Now this C is minimal, D is minimal. Remember? Okay, if I delete this B, let me delete this B. Now you can see who is minimal. Now this is minimal because there is no incoming A's. This is minimal. This is also minimal because there is no incoming A's. Okay, so what you can do? Either you can do C, D, E. This is correct. Or what you can do? You can do D, C, E. This is correct. Yes or no? Is this clear? Okay. Can I do something else? If I don't start with A, then what I can do? I can start with C. This we have already seen. A, B, C, D, E. This is correct. And A, B, D, C, E. This we have already seen. Now, if I start with B, I can start with B, right? Okay, because B is minimal, so I can start with B. Now, if I start with B, I delete this B. Now, which is the minimal element? Can I start? Can I take D? Is D minimal? No, D is not minimal because A is related to D. Okay, D has incoming A's. There is incoming A's, so you cannot take D. Okay, so if I delete this B, then I have to take A. Now, if I delete these two, now again, this C comma D, they are minimal. Okay, so either I can do CDE or I can do DCE. So total answer will be what? Find all. So how many are there? The answer will be 4. Understood? Is this concept clear? Tell me. So very simple point. This is all you have to understand. This is the final conclusion that for any POSET, for any finite POSET, for any finite POSET P, two things are same. What are those? Two things are same. For any finite POSET P, these two things, compatible total order, compatible total order of P, that is same as, that is same as topological order of P. Understood? Let me know. These two things are same. Topological order of P. Okay. Remember, starting with the minimal element that you all know, that you know. Okay, always starts with minimal element. It starts with minimal element that we already know. Why we start with minimal element? Tell me. The topological order, why it starts So this is the note. This is very important that for any finite POSET, if I give you any finite POSET and I ask you what is compatible total order of this finite POSET, then that is same as topological order of this POSET. Okay, very simple. These two things are same. So in the gate exam, if they ask you compatible total order of P, that is same as topological order of P. And remember that to find the topological order of hash diagram, then what you need to do? You need to start with the minimal element. Why? This this topological order, why does it start with minimal element? Because minimal element has no incoming edge. Remember, topological order always starts with element with no incoming edge. So minimal element has no incoming edge. That is the reason topological order will start with minimal element. So all these things you understand. This topic is very simple, very easy topic. Okay, just understand everything. Why these two things are same, that we have already seen. Why topological order will start with minimal element, that also we have seen. So I'm teaching you every concept with proof so that you can understand why these things are happening. For any finite POSET, these two concepts are same. And remember, if you want to find the topological order, then you have to start with minimal element, because minimal element has no incoming edge. Now let's move on. Now this is a question from the Kenneth Rosen book. Very simple. You can read this question. Let me read it. There is a project in a company that requires the completion of 7 tasks. You need to complete these 7 tasks. The question is saying some of these tasks can be done only after finishing the other task. Now the question is saying that task, if task X is related to task Y. Okay, for example, you can see task B that is related to D. Then what should happen? Then D cannot start before B. You can see if task X, read this line. Task X is related to task Y. If task Y cannot start until task X is over. Now the question is simply asking, find an order in which these tasks can be carried out. I want to complete the project. I need to do these 7 tasks I need to do. So tell me, in which order can I do these tasks? Let me know. And the question is already saying that if B is related to D, then you cannot start D before completing B. Or I can say, because B is related to D, so B will happen before D. Okay, or I can say D will happen after B. Very simple. So ultimately, what we need to find out, tell me? We need to find out the topological order. Okay, and remember, these are the minimal elements on your screen. A, C, E, these are the minimal elements because they have no incoming edge. No element is related to A, no other element is related to C, and there is no incoming edge in E. Okay, so finally you tell me, the question is asking find an order. You don't need to find all the order, but what you can do, you can find an order. For example, this order you can do. Okay, I can start with task A. Okay, delete this task A. After deleting task A, can I do task B? Tell me. After A, can I do B? I cannot do B because after A, B is not minimal. Remember, B is not minimal because C is related to B. So B is not minimal. So you can easily see this was the minimal. So I can start with A. After that, I can take E because E is minimal. First, I'm deleting this minimal element. Then these are the minimal elements, C, E. So I can delete E. Okay. Now you tell me. Now I have to delete C. Now tell me, if these 3 are gone, then who is minimal? Then B is minimal. Then B is minimal. Now if these are gone, now who is minimal? Now D, F are minimal. Okay. So D, F are minimal. Either you can do this or you can do this. These are correct. Of course, you can create more total order. For example, what you can do? You can start with E. What you can do? You can start with E. Then you can take, for example, A, C, B, D, F, G. This is also correct. Okay, is this clear? For example, you can start with C. Okay, you can do A, C, then you can do B. Yes or no? See, if I do AC, if I delete AC, because A, C, they are minimal. If I delete them, now who is minimal on your screen? Now who is minimal? Tell me, who is minimal now? Now you can see B, E, they are minimal, right? Okay, so I can take B. Then if I take B also, now you tell me who is minimal. Now who is minimal? Now D comma E are minimal. Yes or no? Now D comma E are minimal. So this is also correct. Okay, and so on. For example, you can do AC, then you can do EB, and then FDG. This is also correct. Okay, and so on. Okay, many more are possible. Is this clear? Many more are possible. So, very simple question, right? In the gate exam, they can give you four options and they can ask you which is correct. Okay, you can easily see. So, basically, you have to find the topological order. And remember, you have to start with minimal element because minimal element has no incoming edge. Okay, now let's move on. This is the solution. You can read the solution. Now, let's move on. So, we have seen what is topological order. I hope you understood. Okay. So this is the conclusion that topological order, that is basically the same as creating total order from partial order. Okay. If I want to create total order from partial order, then what I need to do, I need to create the topological order. So these two things are same. And remember, we already know in our lectures, we have already seen that every finite POSET has a minimal element that we know. Okay, every finite non-empty POSET that always have at least one minimal element. This we already know. In our lectures we have seen that if you have a finite POSET, then it will always have at least one minimal element. Now let's move on. So now on your screen, all the following are same. In the beginning of the lecture, I told you that all the following are same. Now you tell me so far which of them did you understand and which of them we need to study now. So did you understand that the first and three are same? This first number and three number, are they same? Did you understand? 1 and 3, they are same. Constructing total order from partial order, that is same as topological ordering, they are same. Did you understand? They are 4 is also same. Linearization of partial order, yes or no? That is also same. What else did you understand? What else? For example, fifth is also same. Compatible total order, this is also same. Yes or no? So far, did you understand these? 1, 3, 4, 5. But still, one more is remaining. This is remaining, right? Second is remaining. Second, we did not see so far. Did we see? Finding total order that contains a partial order. This we did not see. Okay. Now we need to see that what is this? Okay. Now what we need to see the second point. This is what we need to see. Okay. So I will explain now. Finding total order that contains a partial order means a partial order is given to you and the question will ask you find total order that contains this partial order. What this means? Containing a partial order, what this means? This is what we need to study. So let's start with this example. Let me give you a partial order. Okay, this hash diagram, consider this hash diagram A, B, C. Okay, this is a partial order, right? Okay, I can say this is a POSET. Very simple. Now you tell me, find a total order that contains this partial order. Did you understand? Read the question. Find total order that contains this partial order. Now, what this contains means, what this word means, let me explain. Okay. Now, here you can see this is your partial order. A is related to B, A is related to C. This is your partial order P. Let's call it POSET P. Correct? Okay. This is your POSET P. So tell me what is P now? In the set representation. In the set representation, what is P? A is related to A or not? Yes. A related to B? Yes. A related to C? Yes. B related to B? Yes. C related to C. Is this correct partial order? Set representation. Tell me, is this correct? This is the set representation. Now I want a total order which contains this partial order. Now I want a total order T which contains this partial order. Is this clear? I want a total order T such that T must be superset of P. Are you getting my point? Yes or no? Is this clear? Basically, I want a total order T such that T contains P. T contains P. Okay, I want a total order which is a superset of this P. Contains means what? Contains means subset. This word contain. This is same as subset. Okay, so remember, T contains P. That means P is subset of T. Is this clear? Very simple point. This POSET is given to you. This is the set representation. Okay, A is related to A because of reflexive property. Every POSET is reflexive, antisymmetric, transitive. So we got this POSET. Now I want what I want. I want a total order. This is what I want. I want a total order which contains P. Okay, I want a total order which contains P. Means P is subset of T. Okay, so you tell me. I want total order which contains P. Total order containing P. Total order T containing P. Containing P. It automatically means this P will be as it is. Okay, yes or no? This, I am finding this T. Okay, so this P will be as it is, right? This P will be as it is. Understood? This P will be as it is because T contains P. T contains P. Okay, so this P will be as it is. This is your P. But is this a total order? So can I stop here? Can I stop here? Can I stop here? No, this is not a total order. This is same as P, but this is not a total order. Some extra things I need. Okay, some extra things I need. Now you understand. Notice that. Notice that in this total order, I will create the total order hash diagram. I will create hash diagram of T. So is it mandatory? Remember, hash diagram will have 3 elements. Do you understand? Yes or no? Total order will have 3 elements only. That you already know. Total order is a chain. So it will have 3 elements. You just tell me one thing. In this total order, a very simple question I'm asking. In this total order, is it possible that A is here, B is here? Is it possible? Is it possible that this type of situation, is this possible? This is not possible. Why this is not possible? Tell me. What is the reason this is not possible? This is not possible because already you can see that A is related to B. Already you can see A is related to B. Yes or no? Is this clear? You can see already A is related to B. So you must have A related to B. This you must have. You must have A related to B. You must have A related to C. So can I guarantee that A will be at the bottom? A related to B, A related to C. So can I say A is at the bottom? Yes, A will be at the bottom. Now there are two things you can do. Either you can put B here, C here. Is this correct? Yes, this is correct. Basically what you are doing, just one more ordered pair you are adding. This is your T. This T is correct. Yes or no? Is this clear? This is one more thing you are adding. Now you got a total order. You can check this is a total order. This entire thing is a total order. You can check. Okay. Is this clear? Or what you can do? Or you can add this. Or you can add this. This is also correct. Okay. So I can call it T1 and I can call it T2. Is this clear? This is new. That's it. Understood? Is this clear? Please tell me. Is this point clear? With this concept, total order contains partial order. Did you understand this? Let me know. A total order contains partial order. Now let me tell you what is happening. Okay, let's see this in an easy way. This is A, B, C. From this, I want to create a total order which contains this. Okay, this is your POSET. This is your POSET P. What I want? I want total order containing this P. I want total order T containing P. Okay, containing P. Now you don't have to create the set representation. Without set representation, you think about it. I want total order which contains P. If I want to contain P, then can I guarantee that I must have A related to B, A related to C? Yes or no? I must start with A, because if I want to contain P, this is what I want. I want to contain P. Containing P means A must be related to B and A must be related to C. So I must follow these rules. A must be related to. So remember, I got this point that I must have A at the bottom. No one can stop it. Okay, A at the bottom, because you can see this is the least element. I hope you are getting the point. I am putting this list element as because this is the minimal. So I am putting this minimal element here. This is minimal element. Okay, now there is B comma C. They are not comparable. Okay, now you can do this. Either you can do this B, C, or you can do this. Either you can do this or you can do this. Okay, now you can easily check. You can easily check whether you do this T1 or whether you do this T2. They both contain P. Yes or no? You can easily see T1 contains P. Is it correct? Is it correct? T1 contains P. You can see T2 contains P. Whatever you have in P, that is also in T1. In P, what you have? Everything that you have in P. In P, you have this. In T1 also, you have this. In P, you have this. In T1 also, you have this. In P, you have this. In T1 also, you have this by transitivity. Yes or no? So everything that P has, T1 also has. Right? So I can say T1 contains P. Also, T2 contains P. Very simple. So, did you make this observation? Can you make this observation that ultimately what we are finding? We are finding the topological order. Is this clear? We are finding the topological order. Let me give you one more example. Find a total order which contains the partial order. I am giving you another example. Okay, focus on this example now. Now let's assume A, B, C. Okay, consider this example now. I want total order which contains this partial order. So tell me, what will happen? This partial order you have A, B, C. This is your partial order. This is your POSET P. Okay, what is this POSET P? Can anyone tell me? In this POSET P, you can see A related to A, B related to B, C related to C. Okay. Forget about the reflexive pairs. You don't have to worry about the reflexive pairs, right? Yes or no? Okay. You don't worry about the reflexive pairs. Okay. Just, okay, there are reflexive pairs. You forget about them. Okay. So I'm writing reflexive pairs, comma. What you have? You have A related to C and B related to C. Yes or no? This is your P. A related to C, B related to C. This is your P. Now you tell me, if total order T1 contains P, if total order T, I want total order T which containing P, which contains P, then is it mandatory that in this total order A should be related to C? Tell me. I want total order which contains P. Total order containing P. Containing P. So if I want a total order which is superset of this, okay, remember T is a superset of P. I can say P is a subset of T. Okay. So if T is superset of P, then can I say A definitely will be related to C? Yes or no? A will be related to C. B also will be related to C. These things must happen. A related to C, B related to C. So can I say that on the top you will have C? On the top definitely you will have C. Okay, but this is not a total order. This is not a total order. So what you need to do? Now either you can do this A, B, C, either you can do this or you can do B, A, C. Okay, correct. So either you can get this T1 or you can get this T2. Is this clear? Please tell me. Again, you can see what is happening. Basically, I am finding the topological order. Did you notice? Basically, I am finding the topological order. Please check. I am finding the topological order or not. These are minimal elements A, comma B. These are minimal elements. Okay. So first I can delete A. Then I have to delete B, C. This is a topological order. This is also a topological order. Is this clear? So this is the final conclusion, that these things are same. Finding total order that contains a given partial order, that is same as finding topological order of the POSET. And this is very interesting result. Yes or no? Actually, I have seen many students, they solve this type of questions, total order containing a partial order. They solve this type of questions, but they don't have the proper understanding. They do not have the proper understanding. Now, did you understand that these two things are same? If I give you a partial order, given a partial order, if I ask you find total order that contains this partial order, find total order which is superset of this partial order, that is same as finding the topological order. Is this clear? That is same as finding the topological order. Please tell me, did you understand this? Let me know. Okay. So very simple. So remember, these things are same. Given a POSET P, given a POSET P. Okay, if I give you a POSET P and I ask you these things are same, the first thing, find total order containing P, find total order T containing P. That is same as what? That is same as find total order which is superset of P, which is a superset of P. And that is same as, and that is same as find topological order of P. All these things are same. Let me know. Is this clear? Please tell me. Okay. So finding total order containing P, that is same as finding total order which is superset of P, that is same as finding the topological order of P. Okay, let's see this example. Find total order which contains this partial order. I want a total order which contains this partial order. So what I will do, tell me. In this type of questions, now what you will do? Now you can just simply find the topological order. Yes or no? Find topological order, find total order that contains this partial order. This is same as finding topological order. Finding topological order. Okay. Now just find the topological order, but the topological order you write in this direction. Okay, because I want a total order. So you find the topological order, and what will be that? Very simple. These are the minimal elements. Correct. Look at this. This is minimal element. This is minimal element. Okay, so I can start with A. Then what I can do? Tell me. After A, I can take B. Then I can take C. Then I can take D. Then I can take E. Just verify this total order. Does it contains this partial order? Verify this. This is your POSET. This is your POSET P. Just verify. Verify. Please verify this. Verify this total order contains this total order T1 contains P. Please verify this. Let me know. Can you verify? For example, see, A is related to E or not? Let me know. In this partial order, A is related to E or not? A is related to E or not? Yes. Is this included in this total order? In this partial order, A is included to E. See, A is related to E. Is this included in this? Yes, this is included. You can see. Okay. Yes or no? You can notice. Can I say this complete partial order, this is included here? Please tell me. Can I say this total order is a superset of this partial order? You can easily see. A related to D, is this included? A related to D. Notice A related to D. Is this included in this total order? Is this included? Yes. Yes, A related to D. For example, B related to C. Is this included in this total order? Yes, B related to C. Okay, you can see B related to C. Okay, yes or no? What extra things are included? What extra things are included in this total order? Tell me some extra things are included. You can see T is superset of P. T is a superset of P. Yes or no? You can see some extra things are included. What are those? For example, you can see that C related to D. This is extra thing. In this total order, this is extra. That is the reason T is superset of P. Yes or no? T1 contains P. Agree with me? Is this clear? Please tell me. A very simple concept. You can see this total order contains this partial order. Everything that you have in this partial order, that is also in this total order. Every ordered pair that you have here, for example, E related to E, that is also here, E related to E. For example, D related to E, that is also here, D related to E. For example, C related to E, that is also here, C related to E. Yes or no? So you can see there are extra things. Yes, in this total order, there are extra things. For example, C related to D. C related to D. This is extra. This is not in this POSET. That is the reason I am saying this total order contains this POSET. This T1 is a superset of this POSET. Is this concept clear? Let me know. Is this concept clear? So this is the conclusion. Is this conclusion clear to everyone? That given a POSET P, if I ask you find total order containing this P, that is same as find total order which is superset of P, that is same as find topological order of P. Please tell me understood. Let me know. So yes, you can verify this is correct. Okay, you can see T1 is this P is a subset of T1. You can verify this. Okay, what other? Can you give me some other? Give me some other topological order. Can you give me some other topological order? Can you give me some other total order which contains this partial order? Yes, for example, I can start with B, then I can take A, then I can take D, then I can take C, then I can take E. This is also correct. Yes or no? So I can call it T2. This is also correct. Okay. For example, you can do this. You can start with A, then you can start with B, then you can take D, then you can take C, then you can take E. This is also correct. Okay. Understood? Let me know. So like this. I hope you are getting my point. Okay. And so on. Tell me one more thing. Okay. Let me ask you one more question. What about this? If I give you this, for example, if I give you this total order A, C, B, D, E. Okay, look at this and tell me this total order, does it contain this partial order? This is your POSET P. I am asking you, this total order, is this correct? Okay, does this total order contain P? Contain P. Does this total order contain P? Tell me on your screen, this total order, does it contain P? The answer is no. Why? Okay, why? What is the reason? Because you can see in P what you have. In P you have many things, but you have this. In P you have B related to C. Agree with me? In P I have B related to C. Yes or no? Do I have B related to C here? Here you can see B related to C is not there. For example, this B comma C, this does not belong to T. Okay. This total order, this does not belong. Okay, let me call it T. So you can see. So this T is not a superset, right? I can say this P is not a subset of T. This partial order is not a subset of this T. And you can easily see this is not even a topological order. You can see this is not the topological order. That is the reason you can see that is the reason this does not contain this partial order. Now, is this crystal clear to everyone? Please tell me. So if I give you a hash diagram and I ask you, give me a total order which contains this partial order, then the answer will be just find the topological order. The topological order will contain POSET. And if you don't find topological order, then that will not contain this POSET. Is this clear? Please tell me. This concept. See, with proof, I'm telling you all these things. Are you understanding? Let me know. Please tell me. Is this clear to everyone? Anyone has any doubt? So this is the note. Look at this note and tell me, did you understand? Finding total order that contains a partial order. That is same as finding topological order. And that is same as what? And that is same as finding total order which is superset of partial order. Yes or no? That is same as finding total order which is a superset of partial order. Of POSET. Okay, all these things are same. Now let's move on. So this is our final thing. We started our lecture with these 5 points and now we have proven. Are you comfortable? Now can you say that you have understood all these things? Why all these things are same? For example, why this is same as this? Why this is same as this? Okay, tell me. Can you say that all these things are same? Means constructing total order from partial order, that is same as finding topological order. Similarly, compatible total order, that is same as topological order. Linearization of partial order, that is same as topological order. And finding total order that contains a partial order, that is same as topological order. So ultimately, in all these things, you just have to find the topological order. Okay, ultimately, this is what you have to find. So remember, same question they can ask you in 5 different ways. This is the beauty. They can ask you same question in 5 different ways. Okay, and what is sixth way? What is sixth way? Please tell me. There is sixth way also. What is that? There is sixth way, that find total order which is a superset of partial order. Yes or no? This is sixth way. Find total order which is a superset of partial order. Okay, that's it. So all these things are same. 1 to 6, all these things, they are same. Now let's move on. Now let's solve this gate exam question. This is gate 2024. Very recent question. A partial order is given to you. This is the partial order. The question is asking the number of total orders which contain P. Now this is a very easy question for you. The number of total orders. How many total orders contain P? We have already seen that. This result we have already seen. If you want to find total order that contains a partial order, that is same as finding the topological order. And to find the topological order, you will start with the minimal element, because minimal element does not have any incoming edge. That is the reason. To find the topological order, you will start with minimal element. So this is the point. The question is asking, read this question, the number of total orders which contain this partial order P. And we have seen this result, that finding total order that contains a partial order is same as finding total topological order of this POSET. Okay, so now you find this. What will be the answer? So this is the POSET that is given to you. You can see partial order defined on set 1, 2, 3, 4. Okay. These are the reflexive pairs, right? Look at this. These are your reflexive pairs. Okay, because X related to X. X related to X, where X belongs to 1, 2, 3, 4. So these are your reflexive pairs. And these are some extra 1, 2, 3, 2, 3, 4. So your first you create the hash diagram. So what is P hash diagram? Hash diagram of this partial order, what that will be? That will be 1 related to 2, 3 related to 2. Okay, so you can see 1 is related to 2, 3 is related to 2, and 3 is related to 4. Okay, 3 is related to 4. This is the POSET P. Now tell me, how you will find the total order containing this P? Now these are all you have to do, just find the topological order. Very simple. Okay, all you have to do, just find the topological order. So you can see these are the minimal element. This is minimal element, this is minimal element. Okay, so I can start with one, no problem. I can delete this minimal element. If I delete this minimal element, now I have to take 3. Then after deleting these, either I can take 2 comma 4, or I can take 4 comma 2. Yes or no? So two topological orders I got, T1 T2. What else I can do? I can start with 3, because this is minimal element, this 3, this is minimal element, so I can delete this 3. After deleting this 3, what are the minimal elements? Tell me. If I delete this 3, now what are the minimal elements? This element 3, if I delete, now what are the minimal elements? 4 comma 1. Now 4 comma 1 are the minimal elements. I can take 4, then 1, then 2, or what I can do? I can take 1, then either I can take 2 4, or either I can take 4 2. Yes or no? Is this clear? Tell me. So finally your answer is what? T3, T4, T5. Okay, this is your answer. Your answer will be 5. How many total orders contain P? The answer will be 5. All these 5 total orders, they will contain P. You can easily see T1 contains P. You can see T2 contains P, and so on. T5 contains P. Similarly, this T3 contains P, and this T4 contains P. So all you have to do, just find out the topological order. Is this clear? Just find out the topological order. Let me know. Is this clear to everyone? Please tell me. So the number of total orders that contain P, that will be 5. In this question, all you have to do, just find out the topological order, because remember, finding total order which contains a partial order, that is same as finding topological order. These two things are same. Now let's move on. Now let's solve this question. This is another GATE exam question, GATE 1997. A partial order is defined on set S. This is set S, X, A1 to AN, then there is Y. So this is set S. And the question is saying that X is related to AI for all I. AI is related to Y for all I. And what this question is asking, look at this. The number of total orders that contains this partial order. Tell me what will be the answer. The number of total orders on this set which contains this partial order. This will be same as what? The number of total orders containing this partial order. This is same as finding topological orders. Yes or no? We have already seen with proof that this is same as finding topological ordering of the POSET. Is this clear? Let me know. Very simple. So finding topological orderings of the POSET, because we have already seen, if you remember, that finding total order that contains a partial order, a given partial order. So if you want to find total order which contains this partial order, that is same as finding topological order. Okay, and remember, when you find the topological order, then you have to start with the minimal element, because minimal element has no incoming edge. Your topological order will always start with element which has no incoming edge. That is the reason topological order will start with minimal element. Okay, now you solve this question. The question is saying you have a partial order defined on this set XA1. This is your set. Okay, you have X, then you have A1 and so on AN, and there is Y. The question is saying N is greater than equal to 1. Okay, because basically you have at least one A. Okay, what this statement means? This statement means you have at least one A. At least one AI you have. Okay, because n is greater than equal to 1. Now the question is saying, read this, x is related to all ai for all I. The question is saying that this x is related to ai. X is related to ai for all I. For all I means x is related to all of them. Okay, remember x is related to all of them, a1, a2, a3, an. Also, the question is saying that ai is related to y, again for all y, for all I. See this, see this, that ai is related to y for all I. So, first you create the hash diagram of the POSET. What will be the hash diagram? Hash diagram of POSET. What that will be? Let's create the hash diagram of the POSET. Very simple information that x is related to every ai. Yes, a1, a2, a3, an. X is related to all of them. See, the question is saying x is related to all of them. You can see this. X is related to ai for all I. So x is related to a1, a2, a3, and so on an. And the question is saying every ai is related to y. Every ai that is related to y. This is the hash diagram. Yes or no? Is this clear? So we got hash diagram first. Now what the question is asking? Now the question is asking, this is your POSET P. Now the question is asking, how many total orders contain this P? Total orders containing P. What that will be? Total orders containing P. Let me know. So if I ask you how many total orders will contain P, so total orders containing P, that is same as topological orders of P. That is same as topological orders of P. Just find out topological orders of P. Okay, so tell me, what will be the topological orders of P? Very simple, topological orders. What that will be? See, this is the minimal element, right? Yes or no? This x, this is the minimal element. Okay, so you will start with x. There is no other choice. We have to start with x. And tell me, can I guarantee at last y will come? Can y come before something? Like, is it possible that y can come before last? No, 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 no. Because y must come. Y must come at last. Because you can see all of them are related to y. All of them. You can see. You can see all of them are related to y. So y should come at last. So I can say that y will come at last. Okay. I'm finding topological order. So first x will come. At last y will come. Now you tell me, in between, they can come in any order because they are not comparable. For example, a1, a2, is there any order between them? A1, a2, a1, a2, is there any order between them? No, there is no order. So remember, once I delete this x, notice, once I delete this x, if I delete this x, now these things can come in any order. So n factorial orders. Once I delete this x, now look at this. These n elements can come in any order. So here n factorial orders. Here you can have n factorial orders. So your final answer will be what? That will be n factorial. Answer will be option A. Is this clear? Let me know. So very simple gate exam question, gate 1997. Remember, the question is asking how many total orders contain partial order. So remember, total order containing partial order, that is same as topological order. So all you have to do, just find out the topological order. This is the hash diagram. From this hash diagram, you can see there are n factorial topological orders. Okay, you will start with this minimal element x, then these elements you can put in any order, then at last there will be y. So n factorial topological orders are possible. So that is the answer for this question. Answer will be option A. Is this crystal clear? Everything that we have seen in this lecture. Okay. Now let me tell you one more thing. Many students, they can solve this question, but they don't have the proper understanding. Okay. You will find that many students, they cannot tell you why they are finding the topological order. Okay. For this question, like total order containing partial order, for this question, they will find the topological order, but they will not be able to tell you what this actually means. If you ask those students, many students, you can see they will be able to solve. Okay, they will tell you the answer is n factorial. But if you ask them what this line means, total order containing partial order, what this line means, yes or no? This line, total order containing partial order, what this contain word means, they will not be able to tell you. So in this lecture, what we have done, in this lecture, we have seen the complete analysis with proof, with proper understanding, crystal clear understanding of all these concepts. I hope you loved this session. Okay. Now let's solve this question quickly. Tell me the answer. This is MSQ question. This hash diagram is given to you. So this is your POSET. This is your POSET P. The question is saying which of the following total orders are compatible with this partial order? Are compatible with this partial order. So all you have to do, just find out the topological order. So let's find out the topological order. Take this question as a homework. Okay. So please put your answer in the comments. Which option will be correct? Option A, option B, option C, option D. Which option is correct? So this is MSQ question, remember. Put your answer in the comments. Pause the video, solve this question, and immediately write your answer in the comments. Okay. Another question as a homework. Again, you solve this question. Basically, just give total order in two ways. Remember, there can be many total order, but you just have to give two total orders. Give two total orders. Okay. Give any two total orders. So this is your homework. Another very simple. You can just check it out. This is another homework. Find a compatible. Find anyone. Find a compatible total order for this POSET. Okay. This is another homework. So I hope you understood all these concepts, and these are the homework. Let me tell you the summary. We are constructing total order from partial order. In this lecture, what we have seen, how to create total order from partial order. A partial order is given to you. From that, you want to create a total order. Then remember, these things are same. All these things are same. Constructing total order from partial order, that is same as topological sorting. That is same as total order that contains a given partial order. Okay, if you want to find total order that contains a given partial order, that is same as finding the topological order. That is same as linearization of partial order. That is same as compatible total ordering. All these things, they are same. This is what we have seen in this lecture. Okay. Thank you, everyone. I hope you loved this session. This is the complete analysis of this topic. There are two gate exam questions based on this topic that we have done. Okay. So I hope you, in a crystal clear way, you understood this concept. So please press the like button and please share your review in the comments. It will motivate us, and we will bring you more and more lectures of this type on the YouTube, on the Go Classes YouTube channel. So thank you so much, everyone.